Okay, so I'm going to start solving this problem. And as we will see, pretty quickly there's going to be an issue. And when I get to that issue, I'm going to explain what the issue is. I'm going to stop this video. And then in the next video, I'm going to show you the resolution of that problem in a more generic setting than this. And then after that video, I'm going to come back and solve this problem. So the solution of this problem is going to be over 3 videos. And then once we do more problems after this, I'll just do it all in one video. But there's going to be a problem here that I want to focus on. So for me, it's helpful to try to imagine a physical situation that this is modeling. This is Berger's, this should not be U here, this should be a 0. So this is Berger's equation. As far as I know, I don't know if it actually models much of anything in real life. So the reason I say that is because it has a setup of a conservation law for a compressible fluid, but there's no pressure term, which we would assume there to be. But it's a very good, you can think about it. Like you can still think about things that it might represent. And really, when I say I don't know if it represents anything, I'm just showing my ignorance more than anything else. So let's assume that U is the velocity of some compressible fluid, and we'll forget for now about why there's no pressure term. So if we think about what's going to happen here, the initial velocity to the left of 0, the velocity is 2, and to the right of 0, the velocity is 1. So you can imagine what's going to happen here. The velocity over here is going to catch up with the velocity here. So what's going to happen? You've got faster moving water here, slower moving water here. What's going to happen when they collide? Something has to happen. That's basically going to be the problem that arises when we try to solve this. And I'll show you where that arises kind of in the math when we work on solving this. So let's begin. The normal thing that we would do here is by finding a parameterization of the curve gamma, which for these problems, well, for this one at least, is going to be the x-axis, t prime of s. I'm going to write this and move out of the way. T prime of s is going to be the coefficient on the t derivative, which is 1, and t of 0 is going to be equal to 0. X prime of s is going to be the coefficient on the x derivative, which is z. And so x of 0, and also x of 0 is going to be equal to x naught. And then z prime of s is going to be the right-hand side, so that's 0. And then we're going to have z of 0. Remember, z of 0 is just we take this point, x naught 0, and plug it into our initial condition. So it's going to be 2 if x naught is less than 0, and it's going to be 1 if x naught is greater than 0. Okay, so let's begin with this. So I'm going to draw our standard axes here. So this is the x-axis, this is the t-axis. Okay, and let's start thinking about the characteristics. I think typically I have the blue characteristics on the left and the purple characteristics on the right. I'll try to continue that. So we notice what happens if we start from the left. So let's say I've got some x naught here. So I've got some point x naught there. I'm starting to the left of 0. Okay, so I'm going to have t of s is equal to s. Now before I can find x, I need to find z. Z prime is 0, so it means z is constant. So the characteristic that starts here, I know z is going to be constant, and I know it's going to be equal to 2. So that gives z of s is equal to 2. So this gives x prime of s is equal to 2. So then x of s is going to be equal to 2s plus x naught. Okay, now this is strictly for x. This is for x naught strictly less than 0. So if I see what kind of characteristic is going to be, it's going to be a slope of 1/2. So I'm going to have something like this with a slope of 1/2. And if I have other characteristics, it's going to be like that as well. Now, as I was saying, this only is technically for x naught strictly less than 0. But I'm going to draw it for x naught equals to 0, but with a dashed line. That's like the limiting case. So in the limiting case, And we'll see an example later where that this limiting case is a little more challenging to deal with than what I have here. Okay. All right, so now let's do something similar over here. Let's say I look at that x naught. We're starting with x naught strictly greater than 0. Okay, I'm going to write and then step out of the way. Well, t of s is going to be equal to s. Z prime is still equal to 0. Z of 0 is equal to 1, so we're going to get z of s is going to be equal to 1. X prime is equal to z, so we're going to get x of s is equal to s plus x naught. So here we've got x of s is equal to s plus x naught. Now I just want to emphasize here. Here, the slopes, over here I'm going to write the slopes are equal to 1/2, and over here u is equal to 2. So over here u is equal to 2, the slopes are 1/2. Obviously there's a connection here, right? Slopes are going to be 1 over the value of u on the negative x-axis. Okay, so now over here, what are we going to get? Well, the slopes is going to be 1 over the coefficient of s there, or actually the coefficient of t over the coefficient of s, that's 1 over 1. So the slopes are 1. Slopes are 1/2 here, slopes are 1 here. We have steeper slopes over here. So what's going to happen? This is going to happen. Okay. Now, obviously, that slope is way more than 1, okay? But I think these slopes are probably way more than 1/2. These slopes look like they should be about 1 here. Okay, but anyways, this is going to be the picture, and then we're going to have when, I'm going to draw the limiting case when x naught is equal to 0. It's going to look like this. Sorry, I need to do that with dashed lines. Okay, so over here, the slopes are equal to 1, okay? Obviously, the scale here is a little bit off. The slopes are equal to 1, and u is equal to 1 over here as well. Okay, so now we have a problem. If you don't see the problem, pause for a minute to think about it. Okay, but the problem is what happens here. On the purple characteristic, the solution is 1, but on the blue characteristic, the solution is 2. Here we have the characteristics intersecting. And it happens all the way back here at the origin. We have these two limiting characteristics intersect. And if we draw these characteristics closer and closer, these characteristics closer and closer, we see there's going to be a collision point at 0, which corresponds to the discontinuity here. Okay, so what's going to happen is the fluid to the left of 0 is traveling at 2 meters per second. The fluid to the right of 0 is traveling 1 meter per second. So, as soon as we start the experiment, imagine the setup where we have, perfectly 2 meters per second here, 1 meter per second here. What's going to happen as soon as we start the experiment, these waves or this water is going to overtake this water here, and something has to happen. And so what we have here is a case of a multi-valued solution, again, because on the purple characteristics, our solutions are 1, and on the blue characteristics, our solution is 2. So the question that we have to answer in the next video is, how do we resolve this discrepancy? Okay, I'm going to post a paper later today, hopefully, by a guy named Peter Lax. His last name might be familiar to some of you. He was actually here at Texas A&M for a little bit as well. Recently died in May of this year. Well, so he has this paper written for what's called it's called the colloquial name is the Monthly. I'm not sure, maybe it's the Mathematical Association of America Monthly Magazine or something. It's a publication of the MAA. But it's just called the Monthly, and the articles that get published there are meant for the audience is meant to be mathematicians, but it's not meant to be like the type of paper that gets published in a journal. It's supposed to be more expository, explaining something, just kind of a fun math article. So I'm going to post it, and he raises the question, well, what happens when we have this situation? The world doesn't come to an end. So whatever this is modeling, something happens, and we want to be able to have the mathematics that reflects what happens. Because again, something happens. It's not like when you have one faster fluid, overtakes slower fluid, the world comes to an end. And so that's what we're going to look at in the next video.